Thank you for joining today's Vibration Research webinar. At Vibration Research, we get a lot of questions on a variety of vibration-related topics. One that we often hear relates to designing products that are robust against vibration inputs from either the end-use environment that the product must live in, or from vibration that emanates from a product's own operating characteristics. In the past, we have talked a lot about how to confidently develop appropriate vibration tests using the fatigue damage spectrum and other methods, but not so much about how to mitigate vibration problems early in the product development cycle. Today, we are going to talk about a design for reliability concept called the factor of two rule that provides a guideline for avoiding resonance-related failures. We'll talk a little about resonance, what the factor of two rule is, why the factor of two rule works, and we'll provide a couple of examples. Resonance can lead to excessive accumulation of fatigue damage and potential mechanical failure. A good practice is to ensure that component resonant frequencies are at least a factor of two above or below frequencies present in the environment that the component will have to survive. This is what we call the factor of two rule. In thinking about resonance, damping is also an important consideration in any design and comes in three flavors: critically damped, overdamped, and underdamped. In a critically damped situation, the system returns to equilibrium as quickly as possible without oscillating. In an overdamped system, the product returns to equilibrium slowly without oscillating, and in an underdamped situation, the product oscillates with decreasing amplitude, if not driven, but can resonate and potentially become unstable with catastrophic consequences if driven at its natural frequency. To avoid overamplification, even in the underdamped case, the component resonant frequency needs to be well separated from the operational vibration inputs to the system. By ensuring that the natural frequency, omega n, is at least a factor of two away from the system's response, the amplitude and potential rapid accumulation of fatigue and failure are significantly reduced. The plot shown on the screen is a transmissibility versus frequency ratio plot, and it's showing the three cases of critically damped, overdamped, and underdamped. Finite element analysis can be used to simulate and analyze vibration characteristics before building hardware. This is an important step early in the product development cycle. Results of finite element analysis should be confirmed on prototype hardware to ensure that boundary conditions, thermal effects, and material properties are accurate and appropriately reflected in the model. Vibration research has many tools available to perform resonance searches and to validate analytical models. These analyses and confirmations are very important, not only for the product itself, also for any test fixtures that will be used for vibration testing. A vibration test fixture that imparts undesired resonant energy into a product leads to ambiguous test results and must be avoided. Once the design is finalized and analytical models confirmed, it's time to test production intent parts with a representative vibration profile. Let's talk a little bit more about resonance. Resonance occurs when a system's natural frequency matches the frequency of external vibrations or forcing functions. This leads to maximum energy transfer between the environment and the product, resulting in large oscillations and excessively high stress amplitudes. With nowhere for the energy to go, fatigue accumulates rapidly and the product fails. This was dramatically shown in the well-known 1940 Tacoma Narrows Bridge collapse shown in the picture. This phenomena can easily happen in machine bracketry, circuit cards mounted in aircraft, structures subjected to wind and earthquakes, or any other applications where unavoidable operational forces are present. Fortunately, as we will show, much can be done in the design phase of product development to avoid failures due to resonance. In real-world systems, damping is present, which, as already explained, reduces the amplitude of vibrations at resonance. However, if the natural frequency is close to the environmental frequency, even with damping, the system can still experience significant vibration. By ensuring that the natural frequency has at least a factor of 2 separation from any environmental inputs, the risk of mechanical failure is greatly reduced. The response of a system to a dynamic load is characterized by its frequency response function, or FRF. The frequency response function is a mathematical tool used to describe how a system responds to different frequencies of input. It shows the relationship between the input frequency and the output amplitude and phase, indicating how effectively the system transmits different frequencies. Around the natural frequency, the response is significantly higher. We'll look at the equations behind this in a moment. In a vibrating system, energy is dissipated among various modes, which are the characteristic patterns of motion that a system undergoes when it vibrates at specific frequencies. Each mode is associated with a particular natural frequency, and the shapes of these patterns are called mode shapes. For example, in a beam, the first mode might be a simple bending shape, second mode a double bend shape, and so on. Each mode shape corresponds to a higher natural frequency as the mode number increases. The factor of 2 separation ensures protection from both the primary resonance or first mode and its harmonics, preventing them from exciting the system into rapid failure. For example, in an aircraft wing design, if the natural frequency of the wing is 20 Hz, a factor of 2 separation would suggest designing the wing to avoid operational and environmental frequencies between 10 and 40 Hz. This helps prevent resonance from aerodynamic forces and engine vibrations, ensuring structural integrity and safety. Typically, vibration sources are wideband inputs and not purely sinusoidal. They can have a range of frequencies due to various operational sources and background noise. The factor of 2 rule is conservative and ensures robustness against a broad frequency range. The factor of 2 rule balances the complexity of exact calculations with the need for a straightforward design principle to ensure reliable performance in varying conditions. This conservative approach of maintaining a natural frequency that is at least twice or half the frequency of operational inputs ensures that products will pass vibration testing and survive in the end-use environment. Most systems, as I said, do have some level of damping. The quality factor Q of a resonance system is inversely proportional to the damping ratio zeta. So write that as Q is equal to 1 over 2 zeta. High Q systems have low damping, but are more susceptible to resonance effects. So let's look at a few examples of damping. So an underdamped, when zeta is less than 1, you can think of car suspension systems. So when a car hits a bump, the suspension system, which is composed of springs and dampers, allows the car to oscillate a few times before coming to rest. This provides a balance between comfort, which is less oscillation, and quick stabilization. Another underdamped example would be a guitar string. So when a guitar string is plucked, it vibrates and produces sound waves that gradually diminish in amplitude due to air resistance and internal friction, exhibiting underdamped behavior. Another one would be a mechanical clock. The pendulum in a mechanical clock oscillates with underdamped motion, where the damping force is small enough to allow continued oscillations, but significant enough to eventually bring the pendulum to rest. For critically damped, where zeta is equal to 1, we can think of automotive shock absorbers, which are designed to quickly return the vehicle to a stable state after disturbance, like hitting a pothole, without oscillating. This ensures a smooth ride and quick stabilization. Or we could think of door closers, the mechanism that ensures that a door closes smoothly and quickly without bouncing back. The door closes at a constant rate and settles in the closed position without oscillating. Or a camera stabilizer. The high-end camera stabilizers use critically damped systems to minimize shake and quickly stabilize the camera after movement, ensuring smooth footage. And then the last case, overdamped, when zeta is greater than 1, we could think of Really heavy door closers, so heavy industrial or vault doors with strong closing mechanisms, return to the closed position very slowly and steadily without bouncing. Also, electronic filters, so certain low-pass electronic filters designed to remove high-frequency noise from signals may be overdamped, resulting in slower response times to changes in the input signal. And thirdly, the third example would be a seismograph mechanism. Instruments used to measure earth tremors or vibrations are often overdamped to avoid oscillations that could distort the measurements. The overdamped mechanism ensures the recording needle returns to its original position slowly and without oscillation. Let's talk about the mathematics behind the factor of 2 rule to better understand why it works. I'll not try to get too deep into the math in this webinar, but I will need to show some basic equations. Feel free to ask questions in the chat if you want a more detailed explanation, and I'll be happy to respond to you after the webinar. Fundamental to the whole explanation is the frequency response function, which we talked a little bit about earlier, or as it's called, an FRF. An FRF describes how a system responds to an input signal at different frequencies. It provides information about the system's amplitude and phase response. An FRF shows how the output amplitude varies with frequency. The FRF function can be derived from the equation of motion and includes a forcing function, call it F sub 0, mass, m, natural frequency, omega sub n, a damping factor, which is represented by zeta, and a input frequency, omega. Note that the FRF is related to transmissibility, and that transmissibility is the ratio of the output response to the input response at a particular frequency. An FRF provides the necessary data to calculate transmissibility. The graph that I'm showing is a screenshot taken from ObserView using the transfer function graph. In ObserView, transfer function graphs are essentially equivalent to FRF graphs, as the transfer function graphs are based on measured data, like what is traditionally referred to as a frequency response function, FRF. So for all practical purposes, they're the same thing. These graphs show the measured response of a system in terms of magnitude and phase across a range of frequencies. As such, they provide a practical representation of the system's behavior under real-world conditions, capturing any nonlinearities and noise present in the measurements. They're a good starting point for understanding how well the factor of 2 rule applies to a system. So for a typical lightly damped system, zeta is small, and the amplitude at twice the natural frequency is much smaller than the amplitude at the natural frequency, which is how the factor of 2 rule works. So looking at the equations here, start out with frequency response function, which I just described in the previous slide. And we note that omega equals, when omega is equal to the natural frequency, then the frequency response function boils down to the forcing function over the mass divided by 2 times the damping ratio times the natural frequency squared. So a lot of these terms cancel out when omega is equal to omega sub n. But what's maybe of more interest is when omega is equal to 2 times the natural frequency. So we'll go through the math on that. And just for simplicity of illustration, we'll let zeta equal 0.5. So plugging in that substitution, letting omega equal twice the natural frequency into our frequency response function, and you can follow the math on your own here, but we ultimately boil down to a relationship in which the mass terms cancel out, and the forcing function also cancels out. So the frequency response function of twice the natural frequency divided by just the frequency response function for the natural frequency works out to a reduction to about 3.3%. So by the time we get out to twice the natural frequency, we've reduced the amplitude by about 97%. And that's why the factor of 2 rule works mathematically. So as a function of zeta and q, since q and zeta have an inverse equivalence, we can express that amplitude reduction factor in terms of either damping or the quality factor. So in terms of damping, it'd be 2 zeta over 3.004. And in terms of q, that works out to just 1 over 3.004 times the quality factor. So let's look at an example, an automotive example. In automotive applications, engine order frequencies are harmonics of the engine's rotational speed as well as firing frequency, which varies with the number of cylinders and the type of engine cycle, so a 2-cycle or a 4-cycle engine. So in this example, let's consider a 4-cylinder automotive engine that idles at 800 RPM, generally operates around 2000 RPM, and has intermittent peaks at 3,500 RPM. Because a 4-cylinder automotive engine fires twice per revolution, the dominant vibration input is second order. So for this example, these translate into frequencies in each of these 3 cases as follows. So idle, we have 800 RPM, and we're firing twice per revolution, and we have 60 seconds in a revolution, so that works out to about 27 hertz. The general operation, they're saying, was at 2000 hertz, or sorry, 2000 RPM, works out to be about 67 hertz. And then the intermittent operation, the occasional, up to 3,500 RPM, works out to about 117 hertz. So by the factor of 2 rule, any components that are going to be influenced by the operation of the engine should have resonant frequencies that are 2 times 117, or they should be greater than 234 hertz. If you're above 234 hertz in this 4-cylinder automotive engine, brackets, controllers, whatever is hanging off the engine, you want to make sure that that resonant frequency is greater than 233 hertz. One area that gets a lot of attention for ensuring robust design against resonant frequencies are large circuit card assemblies that are used for inverters and other power electronics found in battery electric vehicles, as well as marine and aircraft applications. Without an understanding of the operational environment and modes of these systems, it is not unusual for large circuit board assemblies to have natural frequencies that cause large components, such as capacitors or inductors, to fatigue and fall off. For these systems, it is especially important to use analytical methods to predict modes and then to verify in the lab and adjust designs to ensure that resonant frequencies are at least a factor of 2 above the harsh vibration environment that these systems must survive in. There are several ways to adjust circuit card designs to ensure that resonant frequencies are out of harm's way. And most of these rules, they apply to other things besides circuit cards. I'm just using a circuit card as an example here. But increase the stiffness of the board by using thicker materials, optimizing the layout of the board to distribute mass evenly and reduce the overall weight, using finite element analysis to predict resonant frequencies accurately and to ensure that the factor of 2 rule is applied appropriately, performing resonant searches on hardware to confirm the models, and then finally, validating designs with vibration testing using fatigue damage spectrum correlated profiles. So the whole idea here is that we should be able to do analysis up front to come up with designs that are more likely to pass our vibration test and to meet our reliability requirements and survive in the operational environment that they have to survive in. So I'm going to move over here into ObserView for a second. And this first slide, which is just a screenshot, is showing ObserView software. And what I did was I generated a Gaussian noise with a 90 hertz resonance, as well as a 1G 200 hertz sine wave. So we're showing that in the FFT. You can see this resonance at 90 hertz in this Gaussian noise. And then this sine wave, this blue curve, is showing up on the FFT at 200 hertz. So I also just included in here a transmissibility plot and a transfer function to serve as a FRF for this situation. So let me get into ObserView itself here. What I did is I took this Gaussian noise signal, which is in terms of acceleration, g's, and I converted it into a displacement signal. This one. So here is the corresponding displacement signal. And from that, I generated an FFT. And what I wanted to show is that, at 90 hertz, I have displacement of about 0.001 millimeters. And if I go out to somewhere around 180 hertz, as close as I can get here, I've got about 0.003. So mathematically, that works out. That's kind of what we would have expected from what I showed you earlier in the equations, is that doubled the frequency. So we had a resonance at 90 hertz, that doubled it, went out to 180 hertz, and we see that we have about a 96.7, might call it 97% reduction in the amplitude. So the factor of 2 rule, if I follow that as a guideline, does a lot to mitigate the risks of failures due to resonance. So in conclusion, you want to be aware of the end-use environment amplitude, frequency, content, and design life requirements. So these should be coming from the product design documents, as well as measured data to establish what the operational environment is for this product over its life. We use this information to design resonant-resistant products and to develop vibration profiles based on correlated fatigue damage spectrum. We should design critical components such that resonance is separated by a factor of 2 from vibration drivers. Use appropriate Q when performing analyses. As Q increases, the factor of 2 rule has even greater forgiveness. Confirm finite element analysis with sign resonance track and dwell functionality of vibration research software. Validate design with fatigue damage spectrum correlated profile or required standard. And remember to confirm resonant characteristics of vibration test fixtures. Can't overemphasize the need to have a good test fixture when you're running your vibration test. So even if you have a wonderful profile and you have it in good control, or you think you do, if your fixture is not imparting energy properly, then the test results will be questionable. So finally, while the factor of 2 rule isn't derived from a single mathematical theorem, it aligns with the understanding of resonance, frequency response, and the impact of damping on system behavior. It provides a practical safety margin to ensure reliable operation away from resonant frequencies, thereby preventing excessive vibration and potential failure in real-world applications. So that completes our webinar about the factor of 2 rule for designing products that are robust against vibration failures due to unmitigated resonance. So please send an email with any comments or questions you may have about this vibration research webinar or any of Vibration Research's products. We're here to help, so please contact us if you have any questions, and we'll be sure to get back to you. Thank you for listening, and have a great day.